They're actually honored that Professor Pam is with us or is going to present our webinar for this biosphere computing technical committee. Definitely, he doesn't need an introduction because if you are working in this domain, definitely you must know him. But let me give you mm, few words. So he is currently a professor and chair in machine intelligence applied to medicine in the Department of Brain Sciences at Imperial College London, and he is deputy director and group leader in the Care Research and Technology Center at UK Dementia Research Institute, and he is currently an associate editor to IEEE Transactions on Big Data and vice chair of IEEE Special Interest Group on Big Data Intelligence Networking. So his core research is in machine learning, IoT, semantic computing, adaptive algorithm, and computational neurosciences to solve problem and develop new technology for future healthcare system. He has received many uh, international and competitive awards, many leadership awards. So you can visit his profile to get more details. And if you have something like, definitely he is a very senior person and he can guide you in your research as well. So thank you, Professor, for accepting the invitation I here. Over to you now.
Thank you very much. Thanks for having me, and thanks for the kind introduction. I have only one issue. I won't be able to see my screen while I'm in the presenter mode, but please feel free to interrupt me at any time. You don't need to wait until the end if you want me to clarify or if you agree or disagree with anything I say. When Deepak wrote to me and invited me for this talk, I was thinking what could be relevant I can talk, and I tried to take something which sort of looks at the both worlds, looking at the real world healthcare applications, which is related to this community, and also looking at some of the machine learning work we do and how the challenges like in the real world healthcare applications affects our machine learning design. Starting with continual learning, it's just some very brief introduction. I don't know how much you're familiar with, but if you haven't come across the continual learning models, if you look at the existing machine learning models, especially most of the deep learning models, which nowadays are very popular and we hear all about it all the time, often they can outperform the human ability, especially in dealing with large volumes of data, finding patterns in data, and especially long sort of deep neural networks, which are long cascade of linear models with some non-linear functions. They're very good often at looking at sort of finding patterns, looking at the different distributions at the data. The problem with most of the existing machine learning models in terms of especially the design of the neural networks and their architectures is they are not very good at learning something which we take for granted as in human brain. They are not very good at learning tasks sequentially. It means if you have continuous data and your data is non-stationary or your goal is non-stationary, often you face significant challenges in training efficient neural networks. Raya Hatzel and her colleagues at DeepMind, they have a very interesting review related to challenges in continual learning. I highly recommend reading that review if you're interested in this topic. And I have taken some of my slides from their paper, which I've made references in whenever it appears. In principle, if you look at how the machine learning models, especially neural networks, which majority of them, not all of them, work based on sort of gradient descent models, you have a target. You're trying to optimize your model towards the optimum point. In sort of a gradient descent model, your model gradually starts moving from starting usually a random point, starts gradually improving and improving itself to get to the most optimum solution which that model can find for a task. Can you see my cursor when I move it?
Yes, sir.
Okay, great. And here in this case, for example, your model gradually will move in this direction. And if your model is optimum, in each iteration, in each batch you train your model, you move towards this. Now, if your model is given another task, the same model, and if that task has a different distribution, is your optimum point for that task is somewhere else, now your model will start gradually moving from that optimized point it had learned towards the second one, right? And gradually when it starts moving here, your optimum now changes from the initial optimum point to somewhere else. The problem starts now if you wanted your model to learn both these tasks at the same time, to be able to detect like a task related to these points. Basically, you have a competition now between your gradients. Task 1 gradients want to take your model to this way, task 2 gradient model, a task want to take your gradients towards this way. Now, in classic machine learning, deep learning models, you always assume if you can train obviously multi-class models, but your assumption is each class has a sort of a sufficient balanced representation in your samples. It means if you have 10 samples, sample 1, 2, 3 are from class A, sample 4, 5, 6 probably are from task 2. If for a long time one of your tasks doesn't appear in a fixed rate learning model, your model starts balancing towards the other one. It means if you had, I don't know, thousands of samples, suddenly for thousands of samples, task 2 didn't appear, your gradients will start moving this way, and your model gradually will start becoming less optimum for task 2. But in reality, when you create a real-world model, the real world doesn't work like that. The real world is not stationary. You're not guaranteed to have sort of guaranteed distributions or balance between your samples. Take somebody's activity. If you're training a model to learn from people's activity, over time, like people's activity patterns will change due to seasons, due to their health problems. And often when their health problems gets resolved, they might come back to the earlier point. Now, your model continuously will learn to find where is the optimum and will start looking at the outlier from that optimum point. But that optimum itself is contextual and will change over time. And when it changes over time, if your model starts moving towards the other direction and forgets there was another optimum point, basically your model faces a forgetting problem, which I'll talk about all these things. But this is the essence of continual learning, how we can now create models which can continuously learn without forgetting what they have learned. In the common approach in deep neural network to address this issue is to increase the depth of network. If you look at like common neural networks, I don't know, AlexNet, who started like probably was one of the early models for deep neural networks for processing images. There are tens of thousands of the now of this models, but most of them, they start adding more layers into your network. And that's a sensible way of looking at it, because once you add more depth to your network start curving around different sort of distributions around your data, finds the niche areas in much better way, and apply nonlinear activation functions you start creating different regions in your model, and your model will become better and better to converge to more diverse sort of distributions and more diverse models. However, if you keep just adding depth layers, this becomes very complex to train them. Often either they're overfit or you just generally cannot converge to a solution. In any case, your model starts collapsing. If you go the other end of the spectrum, you make your model much smaller. It's often very difficult then to find an optimum solution. Means either you will have a low performance, or your model won't converge at all. Now, the continual learning model is trying to find what is the balance, how much we should add to the depth, how much we should keep the model shallow, and how we can design models which can start learning different tasks by dividing the task into several simpler tasks. That's usually how our brain works. Like if you have learned to open, I don't know, a fridge door, if you want to learn to open a cabinet door, you're not going to learn everything from scratch. You know, the door has a handle, you know, you have to pull it, you know how to move your arm. But if you look at the way we train the neural networks, if you want to train a neural network to open a fridge door, we train for that. If you want to train to open a cabinet door, we train a different neural network. because often our training models cannot break the tasks into simpler tasks. If we can emulate this, we are moving closer to human level of learning. But why do we need this in healthcare? In healthcare, what happens is often you start repeatedly receiving data. Sometimes you will receive the data which your model has never seen before. And I'll give some examples we do in our research. And you have a few choices. Each time you receive new data, you can retrain your model. You can quickly think this is not going to work. The data is going to continuously extend and it's going to be utterly inefficient to do something like that. Or you start looking at, can I find different ways of updating my model, incrementally learn without forgetting what I have learned in the past? And continual learning starts addressing this. Most of the current existing neural network models, they have a problem which in classic machine learning is referred to catastrophic forgetting. And catastrophic forgetting happens when your model starts seeing new data and start adapting to different tasks or different new data, and it starts updating its parameters. Adaptable models, they adapt to your new data, they update their parameters, they start responding to the changes in the environment. But what happens is they start forgetting what they have learned in the past. And when they forget, they face a problem which we call it catastrophic forgetting. It's not a new thing. McCloskey and his colleagues in 1989 had referred to this. There are several new works. There are probably tens of different models and solutions have been introduced for this. But one of the classic examples the DeepMind group did, I think Kirkpatrick and his colleagues did around 2012-13, they trained a model to play a game, an Atari game. And the model started converging, learned to play it, and then they gave the second game. The model initially couldn't play that well. Over time, learned it and started improving and learned the second game. And then they took the second one and gave the first game back. The model couldn't play it anymore because it had forgotten. The parameters had been optimized for the second game. And that's how catastrophic forgetting happens. Now, take this a healthcare scenario. We work in an environment which continuously collect data from people's living environment. We monitor people's movement, vital signs, sleep, and we start creating models which become predictive of adverse health conditions. Now, that environments don't stay fixed. People will have visitors, people's activity changes over time. If the weather is good, people spend more time outside. Sometimes people have infections, they have cold, they have different health conditions, their medication change, and this data continuously changes. Obviously, we would like to train models to start looking at these changes and optimize the performance based on the changes in the environment. What happens is if somebody had an infection and their pattern changed, once they take their medication and they come back to the norm after a week or two, our models have learned to look at what their pattern was over the past week. But what happens is often they forget what was the normal one before this incident happened. And then when people get back to the norm, suddenly the models, they see an outlier and the performance degrades. There are several other examples you can see in learning from looking at people's healthcare records when an event happens, or take a recent instance like a pandemic. A pandemic happens, people in lockdown, they spend more time in the house. Your model learns to that, and then suddenly the lockdowns are removed. Your model is not giving the news or that information, but starts looking at the changes. But suddenly those changes, are there outliers? How the model is going to learn the data is adapted. It changed and adapted to change, adapts to that change without forgetting what they had learned in the past. To make it more real, I'll run through the study we do, and then I come back to these problems and I put it in the context of study we work, and I say how we have been trying to address this and what are the open issues and what are the challenges in creating really clinically applicable continual learning models. In research which we have been running for the past few years, we deploy off-the-shelf sensors and sometimes custom designed sensors for in-home monitoring. We work with people living with dementia, And the idea is to collect data from their living environment and to analyze that data and create predictive models which warn clinicians related to cognitive decline, behavioral changes, or risk of adverse health conditions. The problem is when you collect data from people's home environment, your data is obviously continuous, but it also comes from uncontrolled environment. The data is very noisy and changes over time. And also there is an extra challenge. Again, in classic machine learning, most of the, if you look at machine learning conferences, are dominated by computer vision and image processing because they're more intuitive. There are lots of data available, and you have like large data sets with thousands of and hundreds of thousands of labels and samples. But in scenarios like healthcare, especially if you do in-home monitoring, labeling data and collecting ground truths is very, very resource intensive. Sometimes it's very difficult to do and adds extra burden to clinicians and participants. For example, if you're training a model look at people's physiology, their sleep, their movement, and try to predict if people have an infection or not, going to people's home and taking biosamples or doing infection tests or sending them to a doctor to see whether they already have an infection or not is not an easy task. What happens is often you have a very small number of samples, labeled data to train your model. Now, on top of continual learning problem, you run also the problem of learning with few examples, which goes to a different area like few shot learning, learning with the smaller samples, or learning with imbalanced data, which I won't talk much about it today, but it's also relevant to this research. Back to our healthcare scenario, as I said, we work on dementia care. Dementia is a neurodegenerative condition. Most common form of dementia, which you probably have come across, is Alzheimer's disease. It often affects people's memory, and people start forgetting tasks, forgetting their conversation, and gradually this is a sort of a continuous decline in people's cognitive ability, and slowly this also affects people's physical activity and physical abilities. Globally, around 50 million people in the world are diagnosed with dementia. In the UK, at the moment, around over 850,000 people live with dementia. By 2050, there will be around 130 million people in the world live with dementia. Currently, there is no pharmaceutical solution or intervention to treat dementia. There are some recent ones, they try to slow down the progression, sort of cognitive decline, but generally, the current medicine, they don't really know what causes dementia. Still, there are a lot of unknowns about dementia. Our research focuses on people living with dementia and trying to improve the quality of care and try to predict adverse health conditions in people living with dementia. One of the reasons we do this is adverse health conditions in people with dementia is more often probably than the same age matched group. Like an example of it in the UK, 1 in 4 hospital beds at any given time are taken by someone living with dementia. I work as a part of a large initiative called UK Dementia Research Institute, and we are one of the 7 centres within the UK Dementia Research Institute, or UK DRI, sorry, focusing on care research and technology. Type of things we are trying to find and resolve or use technology to help people living with dementia is trying to find ways of doing personal interventions, trying to understand changes in people's behavior, detecting things like social isolation, detecting like when people's functional and cognitive ability seems to have declined, looking at the sleep disturbance. This is quite a common sort of phenomenon in people living with dementia. Early detection of infections. Often infections, if get sort of undiagnosed in people living with dementia, the infection spreads in their body, it leads to hospital admission, and for people living with dementia, going to hospital and being in an unknown environment adds extra burden to them, to their carers, and to the healthcare services. Looking at neuropsychiatric symptoms, and as I said, looking at social isolation. Just quickly, Alzheimer's Society in the UK did a study a few years ago, and they reported around over 22% of unplanned hospital admissions in people living with dementia were due to preventable causes. Some of the top reasons people with dementia go to hospital are falls, fractures, which often is related to, obviously, to falls, stroke, urinary tract infections, and breathing problems. Also, neuropsychiatric symptoms like agitation, irritability, and aggression is quite common in people living with dementia. Another reason of looking into remote monitoring is the sort of the gap between the access to healthcare. This is a map of England, and it's only shows for the country, but you can imagine this also widespread in any part of the world. People's access to the healthcare services is not homogeneous. There are disparities. Even like within this country, you can see in the map, this shows that people's healthcare, if the people living with dementia, their healthcare has been reviewed over the preceding 12 months. The darker shades of blue shows more of people living with dementia, their healthcare has been reviewed over the past preceding 12 months, and the lighter they become means less and less people. And you see that in, for example, in Somerset, only less than 50% of people living with dementia, their healthcare had been reviewed over the past 12 months. And that adds a huge pressure because often the way then it works, people get diagnosis, they go home, and the next time they see the doctor, maybe when a crisis happens. The crisis could be a neuropsychiatric symptom, they develop an infection, they have a stroke, they feel really unwell, or they get socially isolated. If we can create models and ways of collecting data, continuous data, and trying to be more create personalized way for intervention and predictive, we can avoid these moments of crisis. It means cognitive ability declines over time, but is not a linear decline. There are these moments of crisis when somebody develops an infection, when somebody for any reason goes to hospital. And each time one of these crises happens, adds a lot of burden on people living with dementia, their carers, the healthcare services. We are hoping by collecting continuous data, we can start predicting some of those. Just quickly, the way the setup works, we deploy low-cost sensors. Again, the emphasis on creating something very low-cost, which can generalize to larger population in different parts of this country and different parts of the world. Give a secure environment to send this information to. Part of it could be edge processing, part of it could be cloud computing. We use both models, and to analyze this data, look at the patterns, look at anomalies, generate some alerts, and then we have an in-house software development team, which they have created a platform, we call it Minder, which basically machines will do the repetitive work, constantly get data from different modalities, and then we'll generate alerts, and we use those alerts. We have a care monitoring team. There is a human in the loop here, and our care monitoring team will look at the alerts, and then they'll contact patients, carers, their clinicians. They make a decision based on a clinically validated pathway. And this is a cartoon of what type of sensors you use and how they're deployed. Generally, the sensors are in two categories. Either they are monitoring physiology, like heart rate, blood pressure, weight, hydration, or they're passive sensors looking at like sleep patterns, use of home appliances, ambient light, ambient temperature, or movement around the house. At the moment, we are using passive infrared sensors, and we have a group led by my colleague, Professor Tim Constantino, looking at using radar technologies for that. We also have some living lab environment, which allows our researchers to create sort of synthetic data. We can create a scenario, we have the same setup we deploy in the home, and we can create some ground truth data, create some sort of synthetic samples to initially, if we want to train a model and test the model. Generally, we have a series of data coming. Most of it at the moment comes from devices. We also have some questionnaires. Participants, they do cognitive tests. Also, we have some data which gets added to the system helps us to label some of that data, especially when our care monitoring team interacts with people. They also start, let's say if you have generated an alert, we said somebody had an infection, they will investigate further, they will say that was true or false. By the time they are also doing an intervention and they're trying to identify these cases, they're also labeling our data. The system has an interface, a clinical interface dashboard, which will look something like this. We show the raw data, the algorithms can generate alerts, will appear right observations, and a monitoring team can click on any of these observations, decide to react, add notes, and the system has sort of a mirror of it. With a delay, like by 10 seconds delay, we take all the personally identifiable information and we create a pseudo-anonymized version of this data on a separate platform, which we give it to our users, again, based on security and privacy control measures, but our researchers have access to the label data and the raw data in pretty much near real time. Just quickly to recap, the data we collect are environmental, cardio, activity. All of them I have highlighted in yellow, collected by some means of digital form, automated ways, and questionnaires usually conducted by, these are sort of semi-manually, still stored electronically, but somebody contacts people living with dementia, or we go to their home and we start collecting some sort of clinically validated baseline measures to be able to validate the data we have. Over the past few years, we have collected over 40,000 days of activity data, or 20,000 nights of sleep data. This is not very up to date. This was the statistics around May, June this year. And this shows the diversity of data. This is for the entire population, and these are in million. Like, I don't know, if you look at, for example, bed occupancy data, we have something where 12.5 million items of data from around 140 participants. That shows we have a very large volume of data, what we are collecting this, and this shows the distribution of data. You can see some of them changes over time and it spreads along, and some of them are very focused in when we have collected the data. One-day data across all the samples will look something like this. This x-axis is time of the day, y-axis shows the different features we are collecting in the data. This is from one actually anonymized real home, real person living with dementia from their data. I have taken one specific item from this, and I've highlighted now. This is one day, and I've taken the room temperature and I've shown it across several months. And you can quickly see there is a pattern here. Around this time in summer, you can see the ambient temperature has increased. This is the ambient temperature across all rooms. Now take this across the entire cohort. These are several months of the, several weeks across between 2019 until February 2021. And on the y-axis are the participants. I've just cut the participant IDs to anonymize it. And you can see the heat wave like in summer. And the reason I just took the ambient temperature just to highlight that there is a correlation between increase in ambient temperature and neuropsychiatric symptom in people living with dementia. And just by looking at just one modality and looking at the changes, you can start thinking at how you can start creating predictive models or risk analysis models for different conditions in people living with dementia. Just quickly, this is an example, again, an activity from one home, and across, again, between 2019, January 2019 until sometime in mid-2020. And I've just highlighted when the lockdown happened, and you can quickly see during the lockdown, the activity in the kitchen and lounge started increasing. Again, you can see, you can create models looking at different patterns. Now, in this example, I've shown two different participants. X-axis is time, y-axis is different months of the year. By just looking at the visual representation of this data, and each color shows firing of one sensor. If people do exactly the same thing at the same time of the day, for example, if they sleep at the same time, if the time, this is the time axis, is sleep at the same time, and I don't know, wake up and have their breakfast, go, I don't know, outside, sit and watch TV, do X, Y, Z, and if they exactly do the same time, same thing, you probably around the X-axis, you will see the same colors because at the same time they will start firing. But obviously nobody will have exact routine, exactly waking up at the same time, but they will have, you can find routines in that data, and machine learning models, if you design them carefully, are very good at finding those patterns. Now, by just looking at this too, here you see this participant, nighttime, there are lots of sensors firing from bathroom, from different parts of the house. This shows nighttime disturbance. And more often when people go to bathroom, if you look at this, this could be one sign of urinary tract infection, which is a common case in people living with dementia. Because when people have urinary tract infections, the number of times they go to bathroom increases. And in this participant, you can see that has increased. Again, this is just one modality. Now, when you start adding different modalities, you can start creating more complex models. This is just a timeline of a participant, which I've shown by just aggregating some of our data. What we can do, we can start following up the events that have happened, and we can associate our data to these events, or use our algorithms, for example, to start predicting those, and then later on validate whether that event happened or not. As I said, now the data is noisy, quality can vary because we are collecting data from uncontrolled environments, and there are several factors can affect the data. Seasonal changes, visitors, if they have a pet, sometimes the connectivity issues, you might have some missing values. And in reality, if you want to create a clinically applicable model, you need to be able to cater for all these changes. And these are type of common conditions we are trying to look for. I've taken an example for urinary tract infections. As I said, this is one of the top 5 reasons in people living with dementia being admitted to hospital. This is from the same participant. And you can see on the left-hand side, the participants then didn't have a urinary tract infection. This is the pattern of their activity when they had a urinary tract infection. By just visually inspecting it, see the activity in bathroom and the activity in the living room has increased. This is only environmental data. I haven't shown the physiology here. And again, if you look at the clinical sort of symptoms of urinary tract infections, when people have UTIs, as I said, the number of times they go to bathroom increases. UTI also shows itself with having delirium. And again, when people have delirium, their pattern of movement across the home will change. Now, if we can detect urinary tract infections early, if people diagnosed, early treatment can be very effective. People are prescribed antibiotics. If they take it, usually the infection can go away. The problem is some of the symptoms like getting up at night or delirium can also be mixed up with the symptoms of dementia and cognitive decline itself. People with dementia will have more difficulty in communicating their symptoms. And that's the challenge now for people living with dementia, and why suddenly like an infection, which could be treated simply by some simple measures, can become like an adverse health conditions. Now we've created different various models to analyze this. This is one of our early models, for example. We trained a model, several models looking at how we can create, sort of, you can imagine, it could be a classifier, it could be a risk score analysis, and create models which can alert our clinicians for these conditions. But each time we have trained these models, I've learned generalizability becomes a problem. You train your model, you have a usually small set of samples, and your model learns. But gradually, when it learned, when you start having new data, new samples, the models usually they don't perform well. Now, the challenge is how you create a model which responds well for unseen patterns. And as I said, collecting samples is a especially difficult task. Like, you're not dealing with a machine learning sort of problem, which you have thousands of samples. And also manifestation of symptoms in people could vary. Like, not every patient will show the same set of symptoms in the same settings. Then sort of, if you're looking at it from a machine learning perspective, from a mathematical representation, your distribution of classes are not, distribution of your each class is not centralized in one area. You have a multivariate distribution for your target class as well. The approach we have recently taken is using a semi-supervised model. In a semi-supervised setting, we use a deep neural network, usually a deep neural network encoder, to start extracting features. We extract latent features from the model, and then we use the latent features to create either a classifier or a regression model. That the end product depends on how we're going to use that score, and basically look at the different cases, whether this seems to be a UTI or not a UTI, or give a probability of having a UTI. In this case, we have created a probabilistic model which gives you a risk factor. We'll tell, for example, the model here thinks the person has around, I don't know, 58% risk of having a urinary tract infection. As I showed you, your distribution can vary in a multi-dimensional space. The contours here show your class of distributions could be in different areas distributed in different parts of your multivariate space. And this is like for one real actually data from one real participants, and you can see our model on daily basis creates scores, says what they think, what the model thinks is the risk score for this participant. And here the model seems to be very certain this person has a UTI. And actually here our monitoring team did a validation and validate, and basically what we do, we ask people to go and see their clinician, and they take a urine test, and the urine test validates. And here we have actually validation the person had a UTI. Usually probably the reality has happened here, the validation result, but we always go back from when we ask them to go and see their GP. And you can see probably they have started a treatment here. And if the treatment was effective, the risk scores goes down. Obviously, I've taken a very successful example, but there are cases also your model can terribly take it wrong, especially if it faces with new patterns, unseen examples. If your example comes from a distribution which your model hasn't seen before, if you have seasonal effects, how your model starts catering for those. To overcome catastrophic forgetting problem in machine learning, the classic machine learning, usually they are in 4 categories. Either they use regularization, which basically your model starts finding a trade-off between what has learned in the past and what it learns new. In again, mathematical term, usually like one of the solutions, for example, like in EWC, elastic weight consolidation model, they use Fisher information. Basically, they use Hessian space sort of information. Rather than using only the gradient, they try to adjust, don't change the gradients too much. They look at also the Hessian sort of space information and mitigate these changes based on also the parameters they have learned in the past. In a very simple form, you tell your model what seems to be important for your current task, what weights in what neurons seems to be having higher influence in detecting your current class, and then you are learning the next one, next task. You try not to interfere with them too much. You don't change them too much, because you know if you change those weights too much, you are not going to detect your first class well while you are training for the second class. And these approaches often, the change in the task is told in advance to the model. It means you tell your model, I'm now giving you task 2, I'm giving you task 3. But in real world, the changes don't come with warning. Another approach is memory replay. In essence, you take a sort of a representative of your samples, and each time you relay that to your system. Basically, keep reminding your model what you had, type of samples you had in the past. And obviously, when your task grows, when the variety grows, this becomes intractable. Some of the solutions are creating sampling methods. You imagine you can create a sampler, and rather than storing the samples, you store your distribution of your samples, and you take synthetic samples from that distribution. Imagining something like an MCNC. Markov chain Monte Carlo. In dynamic networks, which are sort of more effective, you start creating an ensemble of models, means for each task you learn a new model, and then you start running into this challenge. What happens if the model grows linearly as your task grows? It means your model becomes complex and then can collapse at some point. Or in a simpler form, you start adding more neurons, more connections to your network. But there is a limit to that, how much you can add and where to add and how to add it also is a challenge. Meta-learning is a relatively newer way of looking at it, which you have a master model and you have some inner loops. Inner loops optimize for tasks. Your master model or outer loop starts learning what task each of the inner loops have learned. Basically, your model learns to learn. You create a master copy, which is a sort of is learned based on what your inner loops have learned. Our approach to solve a problem is a combination of meta-learning and some of the dynamic networks. Means basically we try to converge, to take concepts from dynamic networks, adding sort of ensemble of models or adding new neural resources, and also adding meta-learning. We use a continual Bayesian neural network. Basically, our model weights distributions rather than being fixed are sort of a Bayesian, a Gaussian distribution, and the model trains on a new model for each task, but we'll look at the similarities of the task and the distribution. If they are similar, merge them together. If they are distinct, basically adds new resources to model to learn for those tasks. And we have trained that and compared it with some of the other benchmarks. The advantage for this is we also have a pre-processing step. And rather than telling the model the task has changed, we let the model to analyze the incoming data and look at the changes in the distribution to see whether they seem to be similar to the previous task or is a different task. And as I said, if the two tasks in the end, the distributions seem to be similar, the model merges them to one. And if you're significantly different, sort of creates a distinctive representation for those models. Still, your model's complexity grows as the number of tasks grows and the diversity of the task grows, but it's not a linear. You're sort of trying to save some resources if you can, if there are similarities. If they are similar, merge them. If they are not similar, create distinctive ones. Still, the complexity, the model can basically collapse if your complexity increases. Another challenge is in this type of things, most of these models, including when we published it, we had to compare it with imaging data, because most of these models are sort of benchmarked against images. You give different tasks. And as I said, in most of the existing work, not all of them, you tell in advance what you're giving them. You say, oh, my class is now changed from flowers to cars, and your model knows now the task has changed. But learning for healthcare, you're not going to tell your model your data has changed because you don't know. The data comes automatically and you expect your model to learn. Very quickly, when we put this, our model into practice, it looks like this again. We have raw data, our autoencoder extracts some latent patterns from it, and then we give it to a probabilistic neural network, and that model starts learning the distributions. This is one participant with UTI, with a urinary tract infection. This is the same participant on a different day without a UTI. And you can see the model learns different distributions. Each time we have given a sample, we'll look at whether the sample is within the same distribution or is somewhere else in your space. We start creating a new task for a new distribution, or if it was very similar, merges them to two. And as I said, the end product is just a probabilistic representation. We've benchmarked it against several classic machine learning, like probabilistic models, statistical learning models, and also some deep neural networks, extensively looking at different types of combination of deep neural networks. These are the sort of the results we did, but still this hasn't solved the problem. Still, generalization, I believe, is a problem for us, because the real world is constantly changing. Constantly, when you have, like in our study, we have 140 participants, but when you make thousands of participants, the diversity changes, the home settings will change, our data will change. And how you embed this, you need to think really, really carefully, especially in learning models for real-world healthcare problems. You need to look at the balance between sensitivity and specificity. In our case, for us, it's very important we don't miss cases. But if our model has a little low precision, means our specificity is a bit low, we try to carefully design not to increase the burden, but to be able to verify it. In a very simple form, if our model misses somebody had an infection, that could end up in a hospital admission. But if thinks somebody had an infection and it wasn't true, and if we carefully design it, it just could be an extra phone call once a week or once a day. Now, the trade-off between having that extra phone call or missing someone going to hospital is a very careful balance. And usually you have to look at the specific task, specific way of designing it. There is no one rule can be applied to all. And that's when working with users, working with clinicians, working in a real setting becomes very important. And also, I'll come back to this in a minute. Not every learning model is a neural network. The way forward, we think, is looking at pathway-driven networks. Very quickly, the brain doesn't like it. The neural networks, when you give them input, pretty much your resources, the way to start firing, all the neurons get involved, unless the weight for them is zero, which then they are not active neurons. But in reality, the brain doesn't work like that. Brain has very functional areas, different areas of brain. They learn to react to different sensory inputs. And the new generation of neural networks are moving towards this direction, like creating sort of special pathways related to different tasks. I want to go into this, but Jeff Dean at Google has a very nice and interesting blog post about this, and they're an interesting way of looking at it. Also, I wanted to mention most of my talk today was on neural network, but not every model used in real world is based on neural networks. And continual learning can be also in different areas. This is an example. Amir Marzuki is one of my MSc students. He did a very, very interesting work. Looked at our passive infrared sensors firing. Means when the sensor is fired an area of the home, he looked at when the next sensor is going to fire and where. And these are, for example, took this as locations in the home. When the sensor fired in bathroom, he looked on over a week and then said from the bathroom, where will be the next sensor? What is the likelihood of people going from bathroom to bedroom, or what's the likelihood of going to kitchen or to lounge or the hallway? If you look at this, this pretty much is a Markov chain. And then he started learning the entropy across this Markov chain. It means he started learning how much randomness or how much routineness in this. If you know, like 50% is the chance, if you can go from bathroom, for example, to these three locations, and if you have equal chance to go to any of them, your entropy is zero pretty much, because everything is random. There is no information there. But in reality, they are not like that. Our routines and patterns, there are some deterministic or probabilistic factors related to that. And I really started looking at what is the entropy and how that entropy changes over time. That change meant if my activity suddenly became completely unusual, suddenly your entropy will increase. And if I did exactly the same thing I did the week before, my entropy will be pretty much the same. And we use that to look at how changes in behavior affects people's cognitive decline. This is people at different stages of cognitive decline. These are clinically validated scores we have taken from our participants, and we looked at how their entropy changes across different groups. We also mapped it to different events we had in our participants. Here on x-axis, we have the participants. On y-axis, we have different months of the year. And we looked at when we had the events, and we looked at how the entropy changed. For example, here you see there is a high entropy in these participants, and in fact, they had an infection, they went to hospital. In this case, somebody had a heart attack. And we looked at how this changes in people's sort of routine and activities gets correlated with adverse health conditions. One last thing also, complexity always is not good. This is looking at the vital signs, and rather than creating a very complex neural network or continual learning model, one of our colleagues started looking at just a statistical distribution, looked at what is people's norm. Again, on x-axis, you have the participant IDs, patient IDs, and these are the ranges for each of the vital signs we collect. And this is just a simple statistical measure, looked at what seems to be somebody's norm, and then we start looking at how they change from their norm. This model can adapt, can continue to learn, you can scale it up very, very easily. And that was just an example of what I wanted to show to say we don't always need to create complex models. Obviously, in this case, we are looking at single modalities one at a time. That's not applicable for everything. And also this type of solutions, you need to be aware of the outliers, the effect of if you had a wrong measurement, if you had a wrong calibrated device, what could happen. But generally, sometimes simple models can work very well. I focused on here today, but to create a clinical, sort of clinically validated solution, there are lots of other components involved in actually translating that research to real world. We have a large group of professional software developers who take our researchers' machine learning code and translate it to a real world environment, but that's the topic for another day. And as I said, I work as a part of a much larger group, which we have 6 different programs. We are looking at different complementary solutions which will provide care and support for people living with dementia. What I talked today was just a small fraction of what happens in our center. Also, if you're interested, we have a live system. We have a cohort. We have been running this study for a few years. And here there's a video which shows a perspective of the users. There are lots of other things like privacy, security, effect on people's life. I didn't talk about it, but that video captured some of them. It's just tinyurl.com/dementia new horizon, and you can see the video, or you can Google our website and you can find it. And I just wanted to thank, over the years, we have a user-centered design team at Helix. It's just a spin out at Imperial. And also lots of people living with dementia, their family members have helped us to design and refine the system. I just wanted to acknowledge and thank for their contribution. Some links to some of our recent and related work from my colleagues in the group, which I talked about some of them, and what I presented was a contribution from a lot of members of the group, especially Honglin worked on the continual learning model for UTI, which I talked a lot about this. And as I said, we have a professional software engineering team which design basically translate our solutions to real world. Thank you very much. I'll stop sharing my screen, then I can see. And I'm happy to answer questions.
Thank you, and thank you for joining at 1 hour before. So, questions, please. Anyone want to have any question, doubts, want to know anything,
Sir,
more details?
am I audible?
Yes, Sanjit. Yes, please.
Sir, so I would like to ask the question that you had shown us 2 datas, one where the person was apparently normal, and the other when the UTI started, right?
That's correct.
Sir, so I would like to ask that how do you decide at which point you should start monitoring their health so that you can get a normal data and you can get the new data?
So that's a very good point. One clarification I have to make, and you're right, actually nicely picked that one up. UTI doesn't work, starts like this, like one day you wake up and you have a UTI. An infection starts gradually building up. It's like any other type of infections. Then probably I had to be more careful to say, our model thought on this day the risk has increased, but the person could have had UTI the days before, or the infection could have got to a point which needed a sort of a medical treatment. How do we decide? We don't. The data constantly is collected. We deploy the sensors in people's home, and we have a secure system collects data, and the data constantly collected, lots of it in a passive way. We have sensors when people sleep in the bed, read their heart rate, read their breathing rate, read their sleep in and out. The passive infrared sensors, each time people just pass through them, will fire, and this constantly sends data. We constantly collect data. Physiological measurements like blood pressure, weight, hydration, and some of those we collect, or body temperature. We ask our participants to do the measurement at least once a day, and usually they do it in the morning when they wake up. Their devices which they connect and collect that. And obviously you can introduce wearables, and some of the wearable devices will allow you to collect more continuous data, at least related to heart rate and movement as well.
Sir, so like there are certain trigger warnings which have been exceeded. The system informs you that this person might have a risk.
That's correct, but it's much more complex than that because, like as I said, take UTI as an example. Symptoms of UTI could be, not everyone will have, an increased body temperature, delirium. How do you define delirium is a complex thing. What do I mean by delirium? But we are interested in changes in people's pattern of activities, changes in people's pattern of sleep, number of times they go to bathroom. It's not just counting if they went 6 times to bathroom, they have a UTI. Is the model learns what they used to go and whether that has changed, how many times it has changed. And then you start adding multiple modalities, data from physiology, data from an environment, and you train a model which basically ingests a large volume of this data, learns the patterns, and then you give very small number of samples. You say these type of patterns seem to be associated with urinary tract infections. And next time when your model sees those patterns, they start thinking how similar I am to the pattern I had seen before. But when I say those patterns, they are not just in a simple measures of I passed this sensor 5 times. They are the patterns a neural network has learned in a latent space.
Sir, so like it basically calculates entropy, but not specifically.
One of the examples I showed we were using for changes in behavior, we used the Markov chain, which we collected entropy across the Markov chain. And
Yes,
that was just one of the examples in one of the algorithms we used, but not in every single algorithm we use entropy. UTI algorithm doesn't use entropy. UTI algorithm is a cascade of neural network sorts of layers.
So, sir, does it create much difference? Because in the end, we are just seeing that from an initial pattern, how much does the pattern change? So, how much? Basically, I'm asking that how much does it differ across the data, both the systems?
You mean what is the difference between, for example, looking at an entropy model and a neural network model?
Yes, sir. Yes, exactly.
Again, these models are each trained for a different purpose. If you're training a model to learn UTI, I don't think just using entropy measure will be sufficiently sensitive or sufficiently be able to capture the diversity you need, or you might need to create multiple models of a range of models which are going to be then intractable to train and trace them and update them. But if you're looking for someone's day-to-day routineness in their activity, and you're interested in the changes of the activity, maybe the entropy over a Markov chain could be one way of doing it. It's just only one way of doing it, I have to say, and it's not the only way. But changes in people's pattern of activity has no direct relation whatsoever to whether they have a UTI. Well, if they have a delirium, they could show it, but you cannot just measure that change and infer people have an infection. There could be hundreds of other conditions that cause it. Then each of those models are different, trained for a different purpose. For example, our entropy change model could be very good, sensitive, and have good sensitivity and specificity to detecting social isolation. Because if you don't see many changes in your model, or you suddenly have a massive change which shows the very reduced level of activity, somebody maybe is unwell, doesn't move around the house, is sleeping, or it's been socially isolated. That can be a good measure, but not necessarily that the same model can be applicable for example, detecting infections.
Got it, sir. Thank you.
You're welcome.
Sorry. Okay, thank you. Thank you so much for the presentation. I just wanted a slight clarification on, I don't know which slide it was, but you said adding a memory replay to your model makes it intractable. Could you explain by what do you mean? How does it make it intractable? I don't get that part.
When I said memory model, we don't use memory model. I was just referring to some of the state of the art. And one of the ways of, like if you look at the literature of continual learning, people use memory. And by memory, what I mean, if your model is going to see different samples, you keep remembering samples, and you're going to replay the samples. But if your model is going to see lots of samples over time, you're not going to be able to collect all the samples and each time replay them, right? If you're training a model and you have, I don't know, hundreds and thousands of samples, each time you're not going to replay the whole thing. And I said, if your sample number increases, by intractability, I meant this computationally becomes sort of a not very feasible way of creating this. That's what I meant by intractable. And the sort of the existing solutions in this category of models, they say, well, we don't need to keep every single sample. We keep representatives of those samples. Now, as soon as you said, I'm going to keep the representative samples, the question is, how do you pick up those representatives? If you're training a model to learn, I don't know, let's take an image example, trains and trucks and flowers, which flowers do you think are going to be representative of your flowers? Some of the models, they train a sampler. And if you're familiar with like Markov chain Monte Carlo, Hamiltonian Monte Carlo, GAN networks, you can train any form of sampler, depending again how much complexity you can afford, how much resources you can afford to create this. And rather than storing every single sample, you have a sampler. And the good thing about samplers, you store a mathematical model. Like say an NCMC sampler is just a mathematical model, and you can draw unlimited number of samples, depends how many you want, will give you samples. But how good and representative they are, it depends on your strategy of creating it.
Okay, thank you so much.
You're welcome.
Ashish, you are asking something?
That's a brilliant question. The short answer is very hard. It's very difficult to do that. The long answer is the approach we have taken, we use a semi-supervised model. In semi-supervised model, we have a very large volume of data, which is unlabeled. And rather than just discarding that unlabeled data, we extract features from that. Like, as I said, you can train any type of autoencoder or any way of feature extraction. And rather than looking at the flukes in your data, which suddenly something changed and you say, oh, this change is related to something, you look at first the time series, you look at the recurrent model. What I forgot also, these models are looking at the time series data, not just looking at single measurements, because your data constantly comes. And we aggregate data based on 3 hours or then a daily basis, depends on each application how you aggregate that data. Then you look at the temporal dimension of the data coming, and you look at large volumes of data and you extract latent features. Then rather than working on raw data and creating your classifiers on raw data, you work on latent representations. Already then you have a new data coming in, you feed that to your autoencoder and you extract the latent features and use them. That compensates for some of the flukes and small changes in your data, rather than just looking at the sort of a noise in your data, a device malfunction. You are looking at the constant steady and what your model has learned to extract from that data. But if your device constantly tries to uncalibrate the data and constantly sends wrong data, you're right. Your model could get affected and could start making miscalibrations, misdiagnosis. We have a new PhD student, his research is exactly focusing on that. How now we can make sure if somebody hacks these devices, if somebody sends the data or the device by miscalibration sends data. And it just goes back to you analyze, again, you start looking at outliers on single modality and also correlation of the modalities and trying to infer sort of miscalibrations or any attacks, any type of attacks based on the changes in your data. Missing values are a different issue now. If your device breaks down and you're missing one modality, you can impute for that, and you can have different samplers to impute for that. Because we aggregate data on like multiple hours, our aggregation act sort of already eats that one up, because if you have a few missing values when you aggregate it, you're interested in aggregated values and we normalize it, then we compensate for that. But there are other issues related to that. If you have an algorithm which is sensitive to the sequence of inputs and your data comes in out of sync, let's say when I aggregate per hour, if I look at just only the time I received, not the time the data was collected, and my data comes out of sync, my model might make it the wrong decision. Then each of this adds another dimension which you need to look at. And as I said, I only focused on a very small niche area of the continual learning, but you're absolutely right. When you translate it, we have different researchers, each of them work on different aspects of it. Like we have a PhD student look at the outlier detection, somebody looks at the safety, somebody looks at the feature extraction, and you're absolutely right. No, your question is a very, very good one, and you're absolutely right. I think your question is in the right direction. Yes, you can do that. And again, as I said, in the 50 minutes I had, I made it I dropped a lot of details of this, and I just showed an end-to-end model design. To my students, I actually tell them I'm not interested in any of these models. What I'm interested in doing first an exploratory data science sort of analysis, and a lot of our researchers first will start doing exploratory data analysis without actually creating the model. And I have to say, one of my colleagues, Dr. Eyal Surek, he's one of our lead data scientists in the center. He's the one who encouraged everyone, and he started this idea of we don't need models. We need people to understand our data first, and the designing models are the easiest part. And I totally agree with him. And you're absolutely right. When you start doing exploratory data analysis, you start extracting lots of interesting information. How these modalities, they get correlated. Can you use one modality to compensate for others? Or can you use two modalities to infer the third one when they are missing? Data imputation models, they will use different techniques of similar techniques inherently in your data to do imputation. If you're interested in filling in missing data, some of the state-of-the-art techniques will exactly do that. If you're using a multivariate Markov chain Monte Carlo as your sampler, which you can use it for your data imputation, your MCMC model will learn a multivariate distribution from your data, which basically looks at the correlation between different features you are collecting. Part of it, I think you can learn by models. Part of it also you can learn by simply feature engineering. One of the most fantastic works has been done with our data. One of Alina is one of our PhD students. She works in a different group with my colleague, Professor David Sharp. Alina looked at our sensors when the door sensors fire when people leave the house. Basically, we say the entrance door is open or closed. And then she looked at whether the inside house sensors, they fire or not. Basically, you can just use this information to infer if people have left the house or they are still in the house. Let's say if your front door shows the door was open, and then you watch the rest of the sensors, passive infrared sensors, you see there's no activity detecting. You can infer people have left the house, right? And then you can use that data to see how long they have been outside the house. And now this is a very, very simple measure. You don't need a deep learning. You don't need continual learning. This is a model can scale to any setting. You don't need to know even the layout of the house. But the fantastic thing Alina did, once you have that information, now you can start building patterns, how much people spend outside the house. Have they come back home at night? Are they wandering? Is the change in the path? You can see you can engineer a feature, and then you can build more complex models on that feature. Yeah. Then I said all this. Yeah. No, I said all this, but forget end-to-end model design. If you're designing a solution, focus on your understanding your data. Anyone can design a model, especially deep learning models. You can just learn any of these tools and libraries and design a model in a week without actually knowing how it works. That's, in my experience, in clinical setting and real world, is useless. Spend most of your time to understand your data. Okay.
Anyone having any question? Um, Maybe. So I think Professor actually explained the things very, very clearly. Like most of people must, audience must have understood the concept or the topic, what is discussed by Professor Bram.
Well,
So
some of the machine learning, I think, papers, they try to make the access, make it very complex. Just add math and layers of math and math.
yes.
I think it's not as complex. It's just, I think part of the science is to make it accessible, not inaccessible.
This is something like you we also follow, just to get into top top venue, we represent our model and stuff in that way. But the presentation was very simple, very, anyone can understand. The flow was gone in that way, like starting defining the problem, motivation to, describing the work. It's really fantastic. And many thanks, Professor, for your time, and I'm really sorry for the mess up. The
It's
calendar
all right. It's all
invitation mess
right.
up
It worked
everything.
out in the end, but I mean,
Yeah.
sorry if you had to wait at the beginning for 10, 15 minutes. I was not looking at my emails.
No, it's okay. Like from our side, it's okay. Like for your side, actually, you have come forward just 1 hour before. Thank you so much, Professor. Thank you
Welcome.
for
Thanks for
this
having me.
wonderful talk, and looking forward to something like close work, or there will be any other event we are doing in this community in near future. Definitely, we'll let you know.
Thank you very much, and look
Thank you.
forward to hearing from you. And if anyone had any other question or you were interested, please feel free to drop me an email.
Yes, just definitely. If anyone have any question, also you can always drop us an email at that, as our technical committee email. Then I will forward it to Professor. Then definitely I will get back to you. Thank you,
Thank you
everyone.
very much.
Thank you, Professor.
Thanks. Bye.
Nice meeting
Thank you. Bye. Bye.